Okay, so we'll be discussing point set topology in this lecture. Point set topology. So when you have backgrounds on topology, it's easier to understand differential geometry, but I did not include that prerequisite, and hence I'm holding a background discussion on point set topology. So before embarking on the concept of a general topological space, let us look at the Euclidean space. R to the n. This is a special kind of topological space. Okay, so let us get started with this special situation to motivate our discussion on a general setup. So first note that this Euclidean space Rn is equipped with the notion of distance between 2 points. Distance between 2 points. Okay. Intuitively, it makes sense, right? So say that 2 points P and Q. Say that we have a point P with coordinates P1, P2, all the way up to Pn, and we have another point Q with coordinates Q1, Q2, all the way up to Qn. Okay. So how do we define the distance between these 2 points? We all know that this is nothing but this guy, right? The Euclidean distance between 2 points in the given Euclidean space of dimension n. Okay, we all know that. So by using this notion of distance, one can define an open ball centered at point P in Rn and of radius r, which is of course a positive number, strictly positive number. And how do we define the open ball using this notion of distance? The open ball centered at P and of radius r is a set of all elements in Rn such that the distance from P to x is strictly less than r. So if you want to draw a picture of this ball, it looks like this. It is centered at P and the radius of this ball is r. And by a dotted circle or dotted sphere, we mean the openness of that ball. Okay, so we cannot reach the surface of the ball. We are not allowed to, because of the presence of this strict inequality. Okay, all right. So this is the Euclidean space. So in the Euclidean space, with the use of this notion of distance between 2 points, we can describe open balls. Okay. Now let me erase this slide. Okay. Now, so if if we have a set such as Rn, it's a set, right? So the initial structure that we have in R to the n is that of a set. So if we equate this set with this notion of distance between the elements of this set, such a set is called a metric space. So this is a set plus the structure of the availability of a distance between two elements of the set makes it a metric space. So the notion of distance between elements of the set makes it a metric space. Okay. So using this notion of metric space, we see that R to the n, or the Euclidean space, is a metric space. Okay. And we can talk about open balls in this metric space using the distance function. By the way, the distance function has a name in mathematics called a metric. So the metric is supposed to satisfy certain properties, and those are called the properties of a metric. Say one of them is triangle inequality, the positive definiteness, and there are other properties. So it's not a topology class, and that's why we are not discussing everything in detail. I'm just touching things very briefly. So we were with this Euclidean space. So we have seen that Euclidean space is equipped with the notion of distance between points that we call a metric, and that way it becomes a metric space. And in this metric space, we can talk about open balls with the help of the metric. Okay. So now we can define open sets in this Euclidean space Rn, which is equipped with the metric, the standard metric that we wrote in the earlier slide. So we can define open sets in Rn using open balls BPR, which means that these open balls are centered at P and they are of radius R. Okay. So how can we define open sets in Rn using these open balls BPR? Let's see how. A set U in Rn, okay, so say that this is Rn and we have any set U, okay, and this will be said to be open. This is said to be open if for every P in U, so if I choose any point, no matter how close to that dotted surface, okay, I should always be able to find an open ball. Okay, so let me write it here. For every P and U, there is an open ball BPR. Okay, what does that mean? So that ball is going to be centered at P, and the radius of that ball would be R, in such a way that that ball is contained in U, such that BTR is contained in U. So no matter how close you go to the surface, the dotted surface, you can always find an R such that that pole centered at P and of radius R is always contained within this set U. Then you call this set an open set in Rn. Okay, so some important facts. The union of arbitrary collection U alpha of open sets is open. Okay, so this alpha is an index taking value in an index set that may be a continuous uncountable set. Okay, say that alpha takes values in 1, 2 in this interval of the real line. So it can take all the continuous values from 1 to 2. Okay, so in that case it's called an index set, an index alpha, and this 1, 2 is called an index set. So this is an example of an index set. It doesn't have to be 1, 2, but so such an example. So an example of an index set is 1, 2. Okay, so an arbitrary collection means it's not even have to be a countable collection. Okay, it can be an uncountable collection. All right. So this was one of the important facts. There is another important fact. The intersection of an arbitrary collection of open sets is not open. So let me give you an example for that. For example, the intervals minus 1 over n, okay, n equal to 1, 2, 3 goes all the way up to infinity. So it's a countable collection of intervals. Okay, so if you want, you can denote this collection like this, and from 1 to infinity this way, the same thing. Okay, so if you choose this collection of intervals, then each of this element in this collection, okay, for various n's is an open set in R, is an open interval, to be more precise, in R. So each element of this collection is an open set in R, but their intersection, it's n, okay, minus n, 1 over n to 1 over n is equal to the singleton 0. So it's easy to see it. So intuitively it makes sense, because this guy, so for n to be 1, this is minus 1, 1, so n to be 2 is negative 1 half is decreasing, so negative 1/3, so the intersection is going to be this point, the region, which is a singleton, but we know that this is not open. In fact, this is closed. Alright? Why is it closed? Because its complement is open. What is the complement of 0? The complement of 0 is minus infinity, union 0 infinity is the union of two open sets which is open, therefore their complement is closed. Okay, so what is true actually about the intersection of open sets? The intersection of a finite collection of open sets is actually open. So we replace an arbitrary collection with a finite collection. Okay, then it's going to be true. So I'm not going to prove it. Okay. So as I said earlier, that it's not a topology course, so we don't have the scope of discussing many things in detail here. I'm touching the things very briefly to give you an idea about what topology means. Okay, so these are two important facts. So one fact is the union of arbitrary collection of open sets is open, and the intersection of a finite collection of open sets is also open. These are all happening in Rn. We're talking about Rn so far. Okay, let me erase it. Okay, so let me summarize what we did so far. The metric D in Rn allows us to define open sets in Rn. So in other words, what does it mean? In other words, given a subset of Rn, we can tell if it is open or not. This situation is a spatial case called metric topology. In Rn. Why? Because we are talking about open sets in terms of the metric D that we defined earlier. Remember that D between Q and P were defined as sum over I equal to 1 to n Pi minus Qi whole square, the 1/2, right? Okay, so this is the discussion on Rn, the Euclidean space. Now we give the general definition of topology on a set X. Definition. Topology. Remember that for Rn we have seen that the union of an arbitrary collection of open sets is open, and the intersection of a finite collection of open sets is also open. So that motivates us to give the general definition of a topology on a given set. Okay, a topology on a set S. A topology on a set S is a collection tau of subsets of S. So what do we have? We have a set to start with, and then we take a collection of subsets of S. Okay, so let me give you an example as we move on. Okay, so 1, 2, 3 is a set. Okay, so we can take the all possible subsets set. Say we're looking for all possible subsets for the moment. Okay, so what are the possible subsets of this set? 1, 2, 3. These are the singletons, and we have two element sets: 1, 2, 2, 3, 3, 1. Okay, then we have the entire set, which is also a subset of itself, and we have the empty set. Okay, so the set of all possible subsets, we know from set theory that is called the power set of the given set. Okay, so tau is something like this. Okay, which is a collection of subsets of the given set. Collection of subsets of the given set. Okay. All right. So now we move on. Okay, it's not working. So topology on a set S is a collection tau of subsets of S containing both the empty set and the set S itself, such that we have seen in the case of the power set as well. The empty set and the total set were there in the power set as well. Okay, and the set S such that tau is closed under arbitrary union and finite intersection. What does it mean by closed? Let me explain. So if you say you have the collection of certain subsets of your given set. Okay, say the power set collection for the earlier set. Okay, 1, 2, 3. Then you have 1, 2, 2, 3, 3, 1. Then you have empty. Then you have 1, 2, 3. There were 8 such elements of that in the collection. Okay, so now these collection has to be closed under arbitrary union, meaning that whatever elements you choose from this collection, you take their union, and that should be in the set as well. So take 1, 2, and 3. Take their union. 1, 2, 3 is also there. You take 3 and 1, 2. Their union is 1, 2, 3. This is again here. You take 2, 3 and 3, 1. Their union is 1, 2, 3 again, which is also in this collection. You take 1 and 2 only. Their union 1, 2 is there as well. So it is closed under arbitrary collection. Union of arbitrary collection. Okay, so there are not many choices here, so arbitrary is not probably the correct word here. Well, it's of course the correct word, but it's more restrictive in this case. Okay, all right. What does it mean by closed under finite intersection? If we choose finitely many elements from this collection and take their intersection, that has to be in the set as well. For example, we choose 1, 2 and 2, 3. Their intersection is 2. 2 is also here. We choose 1 and 3. Their intersection is empty. Empty is here. We choose 3, 1 and 1, 2, 3. Of course, their intersection is 3, 1 itself. It is here. And we choose 3 and whatever 1, 2. Their intersection is empty. It is also here. Okay, so this is the general definition of a topology on a given set. Okay, so let me write it mathematically, continuing on what I have wrote earlier. If u alpha is in the collection tau for all alpha in an index set. I've explained earlier what it means by an index set. In an index set A, then their union is supposed to be in tau as well, alpha in A. So alpha runs through this index set. And if so, this can be an uncountable set, okay? But now we are not taking only countably, a countable set. We need a countably finite set for intersection of open sets, okay? Now, and if u1, u2, un is in tau, see, it's a finite collection, right? You see, it's a countably finite collection. Okay, so it's just a finite collection is enough, right? Then the intersection of ui's, I from 1 to n, should also be in tau. Okay, so these are all motivated by our experiences in the Euclidean space Rn, where we have seen that the union of arbitrary collection of open sets is open, but the union of the intersection of an arbitrary collection of open sets is not open. We have seen an example for that. But what holds is that the intersection of a finite collection of open sets is open. So that motivated us to give this general definition of topology on a given set. Okay, so now, the elements of tau are called open sets. Okay, and the pair S comma tau. So S is the set that we started with, and tau is the collection of certain subsets of S that obeys what we have written earlier. Okay, these things, the closure under arbitrary union and the closure under finite intersection, these things. The empty set is there, the total set is there in this collection. Okay, so if these are obeyed, these are all obeyed, then this pair is called a topological space. Okay, so now there is another terminology of a neighborhood. Neighborhood of a point. Whenever we talk about neighborhood, there will be an associated point of the given set. So a neighborhood of a point in S, the given set, is an open set U containing P. Okay. All right. Now that we know what it means by open sets, we move to the notion of closed sets, which are the complements of the open sets. Okay. So the complement of an open set is called a closed set. Right? Okay, so let Fi, I from 1 to n, be a finite collection of closed sets. Okay. Okay. It's a finite collection of closed sets. So then we know that from the definition of closed sets, S minus Fi, this finite collection, this is a finite collection of open sets, right? And we all know that the intersection of a finite collection of open sets is open, that we discussed earlier, okay, when we were discussing topology on the standard topology on the Euclidean space Rn. Okay. So it holds that the intersection of these sets, okay, is open, right? Now there is a famous law called De Morgan's law from set theory. Let me write it for you here. You should all know set theory, right? De Morgan's law from set theory. If you don't know, then Google it. So by De Morgan's law from set theory, this guy can be written as S set minus union. So it reverses, the intersection becomes union under De Morgan's law. Fi is open, okay? So if this is open, then this guy has to be closed, right? By the definition of closed sets. So what did we find? The union of a finite collection of closed sets is closed. Okay, so the story changes for closed sets. It's not the same as the story of the open sets. We can see it from here. Okay, so now what about arbitrary collection of closed sets? Okay, let's see. So now let F alpha belonging to an index set A be an arbitrary collection of closed sets, okay, with A being an index set. Okay. Okay. Alright. What happens next is that the arbitrary collection S minus S set minus F alpha for all alphas is an arbitrary collection of open sets, right? Since each F alpha was a closed set, so each S set minus F alpha is an open set. So this is indeed an arbitrary collection of open sets. We know that the union of an arbitrary collection of open sets is open, right? Therefore, you need the union of all these sets is open. Now again, invoking De Morgan's law, we see that this is going to be S set minus the intersection, the union becomes intersection, is open. Okay. So since this guy is open, this has to be closed because its complement is open, so it has to be closed. Implies that the arbitrary intersection of closed sets is closed. So this is the conclusion. The intersection of an arbitrary collection of closed sets is indeed closed. Okay. Alright, so we stop the first segment here. In the second segment, we are going to discuss about subspace topology. Okay. So thank you for attending the first segment.